Welcome to the next lecture of Math 120 Linear Algebra. In the previous lecture, we discussed equivalent systems, equivalent linear systems, and how to convert them into echelon forms. Echelon forms in order to convert the augmented matrix. How do we convert it into echelon form? We have discussed it. If you have any question regarding the echelon forms, you can ask me. Today we are going to discuss basically when we convert any linear system into echelon form and then solve by using backward substitution. We also discussed backward substitutions, how to solve linear systems after converting them into echelon form. We used backward substitution and solved the system. This whole procedure is basically called Gaussian elimination method. I told you. So when you solve a linear system by converting the augmented matrix into echelon form and then use backward substitution, this whole procedure is called Gaussian elimination method. So today we are going to discuss reduced echelon forms. And then Gauss-Jordan elimination method. So there are people who are waiting to join the lecture. Let me add them. There's a question in the chat window. Let me see. What are you saying about? Are we done with reduced echelon forms? No, we have only discussed echelon forms. Now today we are going to discuss reduced echelon forms. If you have any question, you can ask me. Yes?
Sir, could we make the invitation link for the Zoom meeting a recurring link? Because वो मसला हो जाता है फिर बार-बार ढूंढने का.
थोड़ा सा kindly can you speak a bit loud?
Sir, link है Zoom meeting का, वो अभी one time होता है ना, क्योंकि एक lecture का है, तो could you make that a recurring link? वही एक ही link use हो जाए बार-बार.
I can do that. I'll do that next time. But let me. So we discussed echelon forms. I'm going to write a matrix, and I will ask you people to tell me whether the given matrix is in echelon form or not. For example, if we have any augmented matrix which corresponds to some linear system, the rightmost column would definitely be the right-hand side of that linear system. If we converted that augmented matrix into this kind of matrix, for example, 0, 1, some entry, some other entry, some other entry, some other entry, this one, and then 0, 0, 0, 1, some entry, and then 0, 0, 0, 0, 0, 1. Now, can anyone tell me whether this matrix is in echelon form or not?
It is.
It is, yes.
Walid.
Yes, sir, it is.
Is there anyone who has confusion about this thing, whether this matrix is not in echelon form? Because you need to verify 3 properties. In each row, the first non-zero entry is 1. It is correct, the first property. The second property is in each successive row, the first non-zero entry is on the right to the first non-zero entry in the previous row. So this is also correct. This is also correct. The third property of echelon form is for each first non-zero entry, you have to make 0 below this entry. So there are zeros below this entry. Okay, there are zeros below this entry, and there's no entry below this one, so we don't need to make zeros here. So these are the three properties. I would suggest you or advise you to remember another property, that if there is some zero row in the matrix, you have to put them at the bottom of the matrix. Okay, if while converting the given augmented matrix into echelon form, if you get some zero row or more than one zero rows, then you have to put them at the bottom of the matrix. Okay, this is not a property, but you have to remember this thing. Now, still this matrix is in echelon form. Okay, this matrix is in echelon form. I have told you the procedure of converting any matrix into echelon form. I hope you remember that procedure. Now, today we are going to discuss the reduced echelon form of a matrix, of the augmented matrix, in fact. In echelon form, it was basically, for example, we have 1 here, 0, 0, 0, 0, and then 1 here. You have some other entries. Okay, so some other entry, and you have 0 here. You have 0 here, 1 here. Sorry, nothing. Some other entry here. 0, 0, 0, 0, and then 1, 0. Some other entry. This one. So this is your matrix in echelon form. If you, in addition to the three properties of the echelon form, if there is another property you include in those three properties, the first property is basically what? This first non-zero entry, these are called pivot elements. Okay, remember this. Pivot entry or pivot element. Okay, the first non-zero entry in each row in an echelon form of a matrix is called pivot entry. And in echelon form, you have to make zeros below each pivot entry in that particular row. If we make zeros above this pivot entry also, means if you make these zeros here, let me change the color of, yes. If you can make 0 here, 0 here, 0 here, 0, 0, and 0, this one. Now, each pivot entry has zeros below it and above it. Okay. Now, each pivot entry has zeros below 1 and above 1. So if we can make these entries 0, okay. Next property is what? Each pivot entry has zeros below as well as above it. If in a matrix, in addition to those three properties, the first property is that each pivot entry has zeros as well as above it, also the zeros. Then this matrix, which is already in echelon form, now this has been converted into reduced echelon form. So this is basically called the reduced echelon form of a matrix. Let me write another example of reduced echelon form, and you people tell me whether the given matrix is in echelon form, reduced echelon form or not. For example, maybe 1, 0, 0, 0, 0, and 1, 0, 0, and 0. maybe. Now, you tell me whether this matrix is in reduced echelon form or not. Anyone?
Sir, it is.
G Waleed.
It is because the fourth property is satisfied.
The fourth property is satisfied because in each row, the first non-zero entry is 1. So this is your pivot entry here, and this is your pivot entry here. Each pivot entry has zeros below and above it. यहाँ पे ये pivot entry है, यहाँ पे above zeros, below zeros. So it satisfies all the 4 properties of reduced echelon form. That is why it is in the reduced echelon form. Is there anyone who has some confusion? Muhammad Abdullah, you said no. Can you talk to me? Why is it no?
नो सर वो बच्चे ने क्वेश्चन जो किया था ऊपर उसका आंसर किया
अच्छा चलो. You got it?
सर लेकिन मेरा एक क्वेश्चन है सर आई हैव अ क्वेश्चन
जी बोले.
सर एचिलॉन फॉर्म में अगर हम किसी मैट्रिक्स को एचिलॉन फॉर्म में कन्वर्ट करते हैं तो वो अपर ट्रायंगुलर मैट्रिक्स होती है
जी. It's kind of upper triangular matrix, but not exactly upper triangular matrix. Upper triangular matrix and lower triangular matrix, we will discuss them after discussing the linear systems. Then you would definitely clear about those things. I shall discuss about matrices, what are types of matrices, what is the inverse of a matrix, how to find it. We'll discuss matrices after discussing the linear systems. Okay. So it is basically a kind of upper, if it is in echelon form, it's a kind of upper triangular matrix, but not exactly. In upper triangular matrix, your diagonals must be non-zero, and all the entries above diagonal should be non-zero. Okay. Below that diagonal, all the entries must be 0. But in echelon form, it is not always necessary that the diagonal entries are not 0, are non-zero. Okay, there is a little difference between upper triangular matrix and a matrix which is already in the echelon form. I hope you get it. So this is in reduced echelon form. Now I'm going to extend it and write some other things. 0, 0, maybe 1, 0, 0. Is it still in the reduced echelon form?
Yes, sir.
So you have pivot entries. Pivot entries, every next pivot entry is on the right to the previous entry, previous pivot entry. And we have zeros below and above these pivot entries. So this matrix is in reduced echelon form. Okay, I hope you get it. Now, let's try with the help of an example how to solve linear systems by converting them into reduced echelon form. What are the advantages of reduced echelon form over the echelon form? Let's have an example of this thing. This one. Let me solve this question for you people. Let me have an example. Maybe this one. You will also help me to solve it. You'll apply, solve the following linear system. Solve this 4x minus 4y minus 8z is equal to 2. And then negative x plus y plus 2z equal to maybe नहीं. यहाँ पे कुछ और कर लूँ, maybe x minus 2y plus 3z is equal to this, and x plus y plus x plus 2y plus 2z is equal to negative 3, and 2x minus 3y plus z is equal to 3. So this is your system, linear system, and we need to solve it by converting the augmented matrix. I hope you know what is augmented matrix. The corresponding augmented matrix is 1, -2, -3, 2, -1, 2, 2, and -3, and 2, -3, 1, 3. So this is the corresponding augmented matrix, which you call A subscript B, where A is the coefficient matrix and B is basically represents the right-hand side vector of the given linear system. Now, what you do in the first step, you try to make the first non-zero entry as 1. So fortunately, it is already 1. We don't need to convert it into 1. What is the next step? We try to make zeros below this entry. Okay, this is your first step. So how can we make it? By using appropriate elementary row operations. What we can do here, R1 plus R2. Okay, and what is going to change? R2. This operation is basically an appropriate operation to make the second entry 0. So after doing the first step, what do we get here? We get the first row will remain same, and the second row, यहाँ पे 0, यहाँ पे 0, यहाँ पे -1, यहाँ पे -1, and the third row will remain same. Now, next operation which we need to make this entry 0 is what? It is -2R1 plus R3. So R3 is going to change this one. And after applying this operation, what do we get? R1 and 2 will remain same. Only R3 will change. So we are going to multiply this one with -2 and add it here. We get 0. -2 and add 4 minus 3, 1. -2, 6 and add here 7. -2 and add here, we get -1. So this is what we get after applying these two operations. Now our target is to make, now this column is clear now. We don't need to disturb this column because the first non-zero entry, we get 1, which is a pivot element, and we use that pivot element to make zeros below it. Now we need to make 1 here in the next row on the right to this pivot entry. But here we have already 0. But we can flip these two lines. 0 यहाँ पे आ जाए, 1 वहाँ पे चला जाए. So in that case, we can make 1 here. So what we do here, we try to apply another operation, which is R2, interchange it with R3. What do we get here? 1, -2, -3, 2, and 0, 1, 7, -1, 0, 0, -1, -1. So we get 1 here now. This is your pivot entry in the second row. I hope you get it. If you have any confusion, if you have any question, you can ask me. Now, next step is by using this pivot entry, we'll try to make 0 below this entry as well as above this entry. Okay. Fortunately, we have already 0 here. If not, we have to make 0 first here. And then we use this pivot entry in order to make this thing 0. This entry, which is above this entry, we have to make this thing 0. So how can we make this 0? We can only, I told you, we can only use this pivot entry to make zeros above and below this entry. So we can only use the second row to make this 1, 0. Otherwise, this column will be disturbed. the entries might get non-zero and will come back to the previous step. So don't do this. In each row, you have to use that pivot entry in order to make zeros below it and above it. Remember this. So now we are going to make this one 0. How can we make it 0? We multiply 2 with row 2, and then we add it into row 1, and the row 1 will be changed. Okay. Now, after applying this operation, what do we get? The second row and the third row will remain same. We multiply this with 2 and add it here. So we have remain. We have 1, we have 0 here. We multiply this thing with 2 and add it here. 214 minus 3 is 11. And we multiply this thing with 2 and add it here. We get 0. This one. Now, the second column is again clear. You don't have to do anything else with the second column. First column is also clear. It has first non-zero entry, you have zeros below and above it. You have second pivot entry, you have zeros below and above it. Now we go to the third line and we try to make this thing 1. How can we make it 1? We just multiply row 3 with -1, we get 1 there. So negative R3 will serve the purpose and we'll have 1, 0, 11, 0, 0, 1, 7, -1, 0, 0, 1, 1. So we get this thing. Now we have this pivot entry in the next row. What we do, we try to make zeros below it as well as above it. But we can only use this pivot entry to make zeros here. Okay, what we do here, 7R3, -7R3 plus R2. This is the correct operation, and R2 is going to change. So what do we get here? 1, 0, 11, 0, and third row will remain 0, 0, 1, 1, and we multiply this thing with 7. We add it here. We get 0, 1. -7 plus यहाँ पे add -7 plus यहाँ पे -8. You get this. Now this entry has become 0. Now we are going to make this one 0. What operation do we need here? -11 R3 plus R1, and R1 is going to change. So what do we get here after applying this operation? The second row will remain same. Third row will remain same. First row is going to change. So this will be 0, 1, 0, 0. And you multiply this thing with -11 and add it here. So you get -11 here. Now, we're done with it. This matrix is in echelon form, sorry, reduced echelon form now. Is this in reduced echelon form? Do you have any confusion?
Yes, sir.
Yes.
Sir, is it in the reduced echelon form? I'm confused because there is -8 and -11 above the one that is in the last row.
यहाँ पे देखें, the first pivot entry is this one in the first row, first non-zero entry. इसके नीचे ऊपर 0 है. Second pivot entry is this. इसके नीचे और ऊपर 0 है. What is? So this is what you require. Third में यहाँ पे 1 है, first non-zero entry, which is pivot entry. इसके नीचे और ऊपर 0 है. Rest. आगे क्या है? आगे कोई row है ही नहीं. You don't have any other pivot entry. After the first non-zero entry, which is a pivot entry, उसके बाद में जो मर्जी हो, you don't need it. ठीक है? सिर्फ pivot entry जो है, जो हर row में है, उसके below and above 0 होना चाहिए. Nothing else. This is what we call reduced echelon form. I hope you get it. If you have any further confusion, you can ask me any question. So this matrix, the given matrix now is in reduced echelon form. Okay. Now, you can write the corresponding linear system in order to solve it. If you write the corresponding linear system which corresponds this augmented matrix, it would be what? X1 is equal to -11, X2 is equal to -8, and X3 is equal to 1. So you get directly your solution. So your solution is what? X1, X2, X3 is what? -11, -8, and 1. So this is the solution of the given linear system, 0.
Weren't we working with X, Y, and Z?
You can take X, Y, Z, maybe X1, X2, X3. अगर original system में X, Y, Z था तो यहाँ पे आप X, Y, Z लिख लेना. It doesn't matter. I hope you know.
सर पहले अगर हम पाइवट मतलब 1 बनाते हैं, फर्स्ट जो नॉन जीरो एंट्री है, मतलब उसको पहले 1 बना के फिर हम जीरोस बनाएंगे तो उससे आंसर पे कोई इफेक्ट तो नहीं पड़ेगा, या हमें पाइवट एंट्री को 1 बना के फिर उसके ऊपर और नीचे वाले ऑपरेशंस को करने पड़ेंगे?
पहले पिवट जो एंट्री है उसको पहले 1 बनाना है. If it is not 1, okay, and then you have to make zeros below it. Okay.
अगर हमने फॉर एग्जांपल लास्ट में जो आपने किया था कि मतलब एंड वाले को 1 नहीं बना के पहले ही आपने बीच वाले रो में ऊपर 0 किया था, तो अगर मैं पहले नीचे वाले मतलब रो 3 में 1 बनाती हूँ और लास्ट में सारों को मैं रो ऑपरेशंस डाल के वो 0 करती हूँ, तो उससे आंसर पे कोई इफेक्ट वगैरह तो नहीं पड़ेगा?
नहीं, doesn't matter. But try to follow this procedure. Okay. This will basically minimize the chances of mistakes in that procedure of solving those linear systems.
Okay, thank you.
Now you can see that there is an advantage of the reduced echelon form over the normal echelon form. And what is that advantage? In reduced echelon form, we get directly the solutions. Okay, we don't have to use the backward substitution in order to get the solution. Okay, you can see that we don't need here the backward substitution. If we try to convert the given matrix into reduced echelon form, we don't need the backward substitution to get the solution. We will definitely get the direct solution from this reduced echelon form. I hope you get it. Someone was talking. Tell me if you have any question. No?
Sir, to sum up, हम सबसे पहले पिवट एंट्री को 1 बना के फिर उसके नीचे zeros फिर उसके ऊपर zeros और इस तरह हम आगे continuously solve करेंगे, right?
Definitely.
And then जब सब कुछ 0 बना दिए उसके बाद हम अगले पिवट एंट्री को देखेंगे.
बिल्कुल. ठीक है. Move column wise forward. First, handle with the first column and then second column, third, fourth, and so on. Move with the columns and with your pivot entries. पहले रो में आप पहले एंट्री बना लें, pivot entry उसके नीचे और ऊपर 0 अगर बनते हैं तो बना लें. And then move to the second row and then work in that column. Go column wise. Okay?
Sir, I have a question.
जी बेटा.
Sir, right now we are doing reduced echelon form, right?
जी.
तो सर जो पिछला वाला किया था जो हम जिसमें we did backward substitution, so उसका क्या फायदा? तो shouldn't we use reduced form in all the equations we do, in all the systems we use? या कुछ solutions इससे नहीं होते? Is it possible?
कि देखें computational complexity जो है वो बढ़ जाती है बहुत. Whenever you have 1 million by 1 million system, ठीक है, the weather predictions के जो systems होते हैं ना, ठीक है, जो आपको मौसम का हाल बताते हैं, वो बहुत बड़े areas पे हमने कुछ मतलब बहुत सारे points पे ना, वो हर point पे एक linear system बनता है. They are basically, you can say, million by million linear system. They have million unknowns and million equations. How do you handle them? In that case, you cannot simply use these methods, Gaussian elimination method and Gauss-Echelon method, because they involve a lot of computations and they require a lot of computational power as well. There are more efficient methods than these methods. These are basically starting methods, which I told you, in order to handle linear systems. So solving these linear systems, they require a lot of operations, which takes a lot of time. So you need to be efficient in solving linear systems. For example, एक तो मैंने आपको वेदर प्रेडिक्शंस के सॉफ्टवेयर्स का बताया कि उसमें जो मैथमेटिक्स यूज होता है उसमें मतलब 1 million by 1 million लीनियर सिस्टम तो एक नॉर्मल सी बात है, इससे बड़े लीनियर सिस्टम भी होंगे। तो इस तरह के इस मतलब वाइड स्केल पे अगर आपने लीनियर सिस्टम्स को हैंडल करना है तो you'll never use these methods. These are elementary methods for solving this. And even backward substitution, okay, involves less number of steps to basically get the solution, as compared to you have more operations to make zeros above the entries as well. So it depends on the situation. If you have a 3x3 system, 4x4 system, 10x10 system, you can apply always reduced echelon form. There's no problem because it requires not much power, or it involves it doesn't involve many operations. So it depends first thing on your situation. What are you working for? What is your practical problem for which you are trying to solve the linear systems? It depends, in fact, on that thing, which method you prefer to use. Of course, every method has its own advantages and disadvantages. I hope you get it. Waleed was talking.
Yes.
Okay.
Yes, sir, I get it.
You got it? Okay. Now this is what we call all this procedure in which we, for a given linear system, we write an augmented matrix and then we try to reduce it into a reduced echelon form and get the solution. This whole procedure is called Gauss-Jordan method. Okay. Actually, Gauss gave the method of echelon form and Jordan extended it to the reduced echelon form. So that is why this is called Gauss-Jordan elimination method. I hope you get it. Now let me take another example. In this example, we get a unique solution. You can notice here that the coefficient matrix has been converted into what? What is this? The coefficient matrix has been converted into what?
The unit matrix.
It's an identity matrix. What is this? What is identity matrix? You notice, yeah, identity matrix is the matrix. It has ones in the diagonal and off diagonal, all the entries are 0. Okay, this is basically an identity matrix. Yes, let me explain you. We write I3. I3 means it's a matrix of order 3 cross 3. Okay, I3. If I write I2, it means I'm writing an identity matrix of order 2 cross 2. If I write I4, it means I'm going to write a matrix of order 4 by 4 whose diagonal has entries 1 and all other off diagonal entries are 0. I think we do. What is this? We also call it unit matrix. It's not unit matrix. We call it basically identity matrix. Unit matrix, you can say that a matrix having all entries as 1. So don't confuse it with the unit matrix. So identity matrix is that matrix. If we multiply this matrix with any other matrix, we get the same matrix. Either we multiply it from right hand side or if we multiply it from the left hand side, we get the same matrix. It's a kind of identity element you discuss in addition. What is the identity in addition of numbers? It's a 0. What is the identity in multiplication of numbers? It's 1. A number which doesn't change after adding or multiplying with some other numbers, that is basically called the identity under that binary operation. So matrix identity is basically this matrix. This is identity matrix. It doesn't change the other matrices if we multiply this identity matrix with other matrix, either from right or from left. The matrix would remain same. So this kind of matrix is called identity matrix. I hope you get it. So remember this. This has very strong relationship between the uniqueness of the linear systems. For example, if we try to convert any augmented matrix, which is whose coefficient matrix is a square matrix, if we try to convert it into reduced echelon form, and it is converted into identity matrix, then that linear system must have unique solution. Unique solution means only one solution. It cannot have more than one solution. Yeah. I will discuss these things more in more details later on when we'll discuss inversion of a matrix, how to find the inverse of a matrix.
Sir, could you please explain the last point again?
What one?
सर ये जो लास्ट में आपने एक पॉइंट बोला यूनिक सॉल्यूशन
If the coefficient matrix in augmented matrix में जो coefficient matrix होता है, if that matrix has been converted into the identity matrix, ठीक है? When you try to reduce it into reduced echelon form, if we get the identity matrix, then the linear system must have unique solution. Okay, and the coefficient matrix must be non-singular. Coefficient matrix must be non-singular. It means its inverse exists, and the determinant of that matrix must not be 0. These are all results we'll discuss later on. Now, let's take another example in which we can see that there might exist infinite many solutions after converting a matrix into echelon or reduced echelon form. Let me write some example from the lecture slides, maybe. Yes, there is an example on slide number 9, lecture 2. We try to solve this linear system by using Gauss-Jordan elimination method. So the linear system is 2x3 plus 7x5 is equal to 12. And then 2x1 plus 4x2 minus 10x3 plus 6x4 plus 12x5 is equal to 28. And then 2x1 plus 4x2 minus 5x3 plus 6x4 negative 5x5 is equal to negative 1. So now you have to solve this system. Non-singular, yes. Non-singular matrix in the previous case. Now, sorry. Now this is our linear system. We need to solve it by using any appropriate method, either by using Gauss elimination method, Gaussian elimination method, or Gauss-Jordan elimination method. What you do here, you write the corresponding augmented matrix. X1 has no coefficient, X2 has no coefficient, so 0, 0, negative 2, X3, X4, no coefficient, X5, 7, and the right hand side is 12. Then 2, 4, negative 10, 6, 12, and then 28, and 2, 4, negative 5, 6, negative 5, negative 1. So this is your linear system. And the corresponding augmented matrix is this one, AB. Now, we'll start with the first row. We have to make first non-zero entry in the first row 1. Can we make it by using any appropriate operation here? Because it is already 0. So how can we make it?
Where we interchange rows.
Yes, it is possible to make 1 here. We can interchange rows in order to make 1 here. So what we do here, R1, we interchange it with R2. Okay. What do we get here? 2, 4, sorry. 2, 4, negative 10, 6, 12, 28. And then 0, 0, negative 2, 0, 7, 12. And then the third row will remain same. Okay.
तो इनको swap क्यों किया?
We have interchanged these 2 rows in order to get 1 in the first row, first entry. Now what we do here to get 1 here, we divide this whole row with 2. So we do 1 by 2 R1 and we can get 1, 2, negative 5, 3, 6, 14. And then 0, 0, negative 2, 0, 7, 12. And then 2, 4, negative 5, 6, negative 5, negative 1. Okay. Now we have 1 here now. Okay. The first non-zero entry is now 1. We have to make zeros below it in the first step. This is already 0. We are going to make this 1 0. Okay. What we do here, 2R1 plus R2 and plus R3, not R2, plus R3, and what is going to change? R3 is going to change. Okay, this operation, the first 2 rows will remain same, and we get 0, 0, negative 2, 0, 7, 12. And then here 0, negative 2 से multiply करें और add करें यहाँ पे. We get again 0, negative 2 से multiply करें और add करें, we get 5. Negative 2 से multiply करें, add करें, we get 0. Negative 2 से multiply करें, add करें, minus 17. Negative 2 से multiply करें and minus 29. This is what we get here. Now we look at this. Now first row is okay. Now first column is okay. Okay, we get 1 in the first pivot entry, and then we have made zeros below it. Now we move to the second row now. Now we are going to get a pivot element in the second row. We have zeros here below. We cannot flip these first 2 lines in order to get 1, because in that case, this 1 will get it 1 here. So we don't want to disturb the first pivot entry. So you can either interchange these 2 rows to make 1 here, okay, or you can go further to look for the pivot element. So if we cannot get pivot element here because all these 2 entries are 0, so you look for this one. Now we have to get pivot entry here. So we are going to make it 1. How can we make it 1? We just divide row 2 with negative 2. Okay. After applying this operation, we can get 1 here. Yes. Any question? No. Okay. Row 1 will remain same. Row 2 will change 0, 0, 1, 0, negative 7 by 2, and negative 6, because we are dividing with negative 2. So we get here 0, 0, 5, 0, negative 17, and negative 29. Okay. Now, our pivot element in the second row is this one. Okay. Now what we do here, we try to make zeros below it and above it. You need two operations to make 1 0 below it and one operation to make 0 above it. You do it yourself and tell me the matrix. Apply two operations, these two operations, and then tell me the resulting matrix. I'm waiting for it. Now tell me the matrix, resulting matrix, which you have obtained after applying these two operations. Row-wise, tell me the entries row-wise.
1, 2,
1, 2,
-5,
-5.
3. Sorry, I have to do this row now. I have done the other row. There are 2 rows now, so I have done one of them.
Okay, do the second row and then tell me. The second row would remain same. 0, 0, 1, and 0, 0, 1, and then my 0, 0, -7/2, and then -6. So the second row would remain same. Now tell me the first and third rows. If anyone have already done it, you can tell me.
सर उसको 0
I
बनाने के
think
लिए
I have done it.
R1 plus R2 कर देंगे ना?
कौन सा?
सर जो R1 का 5 है, -5 सॉरी, उसको
हाँ?
0 बनाने के लिए हम सिंपली R1 plus R2 कर सकते हैं?
R1 R2 कैसे कर सकते हैं? यहाँ पे -5 है, यहाँ पे 1 है.
Sorry, R1 plus R3, sorry.
You have to use this pivot element in order to make this entry 0 above and below. You cannot use, you can use here, fortunately, but try to follow that procedure which I told you. Okay.
Sir, 5
Fortunately,
R2 plus
you can
R1.
make this 0 by adding the third row. This works here, but it doesn't work always. You have to use that pivot entry in order to make 0 here and then 0 here. Okay?
Sir, हो गया.
जी बोलें. Tell me the first and third rows.
2, 0.
1 सबसे पहले आना चाहिए ना?
1.
First row.
Yeah, 1, 2, 2.
1, 2.
0.
0.
3.
3.
6. No, 3 minus 11.5. Minus 11.5.
Minus
And minus
11.5 and minus 6.
16. 1, 6.
Okay, is this 11.5 is something.
-23/2 आ रहा है.
हाँ ठीक है चले. वही बात हुई ना. 11/11.5. Third row में बोलें क्या है? Third row में what is the third row?
1, 2.
1, 2 कहाँ से आ गया? 0 आना चाहिए पहले.
सर वो मैंने ऐड किया ना.
किसको ऐड किया आपने?
Their third row is 0.
Yes, you tell me. Third row is 0.
0.
0. 0.
0. Again 0.
0.
And then 1/2.
1/2.
And then 1.
1. That is correct. Thank you, Hamza. Now, this pivot entry, we are done with this pivot entry. इसके ऊपर भी 0 है और इसके नीचे भी 0 है. ठीक है? We are done with it. Now we are going to the next row, this one. Now we are looking for pivot entry in this row. So the first non-zero entry is this one. So we have to make it 1. So we are going to make it 1. What we do here, 2 times R3. If we multiply row 3 with 2, we get 1 here. So I'm gonna multiply it here so that I can save my time. So if I multiply it with 2, I can get here, sorry, 1 and then 2 here. Okay. Now we get pivot entry here, 1. What is the next step? You have to make zeros below it and above it by using this particular pivot entry. You can use only this one to make zeros here. Now I would request you people to make zeros here by using this pivot entry, means this row, you make these twos zeros, and then tell me the resulting matrix. I'm waiting for it. Notice that this matrix is now in echelon form, but it is still not in reduced echelon form. Okay, until we have above entry 0 of that of each pivot element, it is not in reduced echelon form. This is the difference between echelon and reduced echelon form.
Sir, it would be
Tell me the entries, please. Let me wait. Let me turn on. Okay, recording is already on. Now tell me the entries after applying these two operations. So what are these?
1,
1,
2,
1, 2,
0,
0,
3,
3, 0,
6, sir. 6.
6. Okay. In the second row, we have 0, 0, 1, 0, 0.
0.
And what is the last entry?
1.
Huh?
1, sir. 1.
1. Okay. In the third row, we have 0, 0, 0, 1. And what is the last entry? 2. Okay. So this is your matrix. And I'm assuming that all the entries are correct. Okay. Now, this is your reduced echelon form matrix, or the given augmented matrix has been converted into reduced echelon form.
Sir,
Now, Gigi,
can whoever solved it also share the operations
can
on the matrix? Also
Can-
share the operations on the matrix.
yes, you have to write the operations, which operation you are going to apply on that matrix. Okay.
7 over 2 T plus R. Like that.
Sorry, could you
जो भी
repeat
है,
that?
आपकी अगर entries इससे different आ रही हैं, तो don't care. I'm assuming that these entries are true. You have to verify them later on. Okay.
सर वो मेरा 7 आया उधर से की जगह।
कोई बात नहीं यार, आप 7 लिख लो, ठीक है?
सर 7 सही है।
If you are confident, तो 7 ही ठीक होगा। चले आप कहते हैं तो यहाँ पे 7 लिख लेते हैं, ठीक है? It's 7 then. So I'm assuming that the 7 is true. 7 is correct. Okay, now we have to write back the corresponding linear system from this augmented matrix because this is already in reduced echelon form. Now, what would be the corresponding linear system here? If we try to write, this is x1 plus 2x2 plus 3x4 is equal to 7, and then x3 is equal to x3 is equal to x3 is equal to 7. Sorry, 1. X3 is equal to 1, and then x1, 2, 3, 4, 5, and then x5 is 2. So this is your corresponding linear system. You can see that we have the values of x3 is equal to 1, x5 is equal to 2, and from this equation, from the first equation, we have 3 variables and one equation. So we have to set 2 variables as a free variables. So I am assuming here that let x2 may be t and x4 is s, where t and s belongs to r. So I am setting them as free variables. In that case, what will be, or x1 will be 7 minus 2, x2 is t, minus 3, x4 is s. So this is your x1. What is your x2? It is t. What is your x3? It is 1. What is your x4? It is s. And what is your x5? It is 2. So this is your solution of that linear system, which is basically infinite many solutions where t and s, they belongs to r. Okay. In the original linear system, you can see that there are Not this one, the above one. In the given linear system, you can see that we have 3 equations and 5 unknowns. Okay. In the given
Sir?
linear system, yes, you would.
Sir, we said that there are infinitely many solutions. This
Yes.
is because we did not know what 2 variables were and we had to set them as free variables.
Yes. Yes. Okay. If you have a linear system, how many unknowns? How many unknowns are there? 5. How many equations are there? 3. So what is the difference here of number of equations and number of variables? It's the difference is 2. So you have to set 2 variables as free variables. You can only find at most, I'm repeating that word, in this linear system where we have 5 unknowns and 3 equations, we can find at most values of only 3 variables. We can find values of at most 3 variables. ज़्यादा से ज़्यादा 3 variables की values आ सकती हैं. कम से कम 2 variables free set करने पड़ेंगे हमें. 2 से ज़्यादा भी हो सकते हैं, 3 भी हो सकते हैं. कैसे हो सकते हैं? अगर आपके पास, for example, this reduced echelon form, if it has this row all the way, it is 0. If you have 1 0 row, then you have to set another variable as free variable. In that case, your x5, you don't get the value of x5 as well. You don't get this value. So you have to set x5 as a free variable as well. Okay, I hope you get it. So in a linear system, if the number of unknowns are more than number of equations, as an example here, number of unknowns are 5 and number of equations are 3. So you can find the values of at most 3 variables. And you have to set 2 variables as free variables. जितने unknowns होंगे, for example, अगर unknowns जो हैं, वो किसी भी linear system में वो 10 है और equations आपके पास 6 हैं. So how many variables you have to set as free variables? At least. How many? Tell me.
4.
4. Yes. At least 4. कम से कम 4. 4 से ज़्यादा भी हो सकते हैं. It depends on the reduced echelon or echelon form of a matrix. Okay. Now, after getting this solution, you can write that solution in the form of parameters or parametric form of the solution. I already told you this can be written as what? You can write it over here: x1, x2, x3, x4, x5. Okay. You in a first vector you write only the constant terms. Constant terms यहाँ पे क्या है? You can write it in this way: 0 plus t plus 0, and then you have 1 here, 1 plus 0 plus 0. You can write 0 plus 0 plus s. You can write here 2 plus 0 plus 0. Now I want you to separate the constant vector. Constant vector क्या है इसमें? 7 0 1 0 2 प्लस वहां से t कॉमन ले लें. t कॉमन लेंगे तो क्या आएगा? कोफिशिएंट्स -2 1 0 0 0, एंड देन प्लस s कॉमन ले लें. कोफिशिएंट्स क्या आएंगे? -3 0 0 1 0. So this is your solution in the vectors form or in the parametric form of that corresponding linear system. I hope you get it. If you have any question, you can ask me. These are basically infinite many solutions. Now, if you get any question, if you have any question, you can ask me. I'm waiting for your questions.
So why do we need to represent it in this form?
This will help us in subsequent topics when we define spaces, spannings, vector spaces, column space of a matrix, row space of a matrix, dimension and basis of the vector spaces. Okay, that's why I'm writing them in this parametric form. Otherwise, this is the solution sufficient, but this form will help us to discuss the further subsequent topics. Now, one more important thing which I wanted to discuss with you people is that while solving this linear system in the previous example, when we obtained what did we obtain here after reducing it into echelon form? Can anyone tell me? While solving this example, what did we obtain? This one. Do you remember? We have converted this matrix into reduced echelon form, and we had obtained 1 0 0 0 1 0 0 0 1, and here it was what?
Minus 11.
Minus 11. Second.
Minus 8.
Minus 8, and third.
1.
1. Okay. Now, after getting this reduced echelon form, you immediately get the solution. X is equal to what? Negative 11. Y is equal to what? It is negative 8. And Z is equal to what? It is 1. You get this solution. Now, what if you have 0 here? What will be the corresponding values?
Won't this mean this is inconsistent?
You have 0 here. 0 Z is equal to 1. What does it mean? It means
It's
0
not
is equal to
possible.
1. 0 is equal to 1, which is not possible. If this is the situation, then the given linear system has no solution. In this case, all the 3 planes in 3D, they might be parallel to each other. They are not intersecting. Or if they are intersecting, then their region of intersection is not common. 2 planes might be intersect somewhere else, and the third plane might intersect somewhere else. They don't have common region of intersection. It means that linear system is inconsistent.
Sir, can we say that they meet transversely?
We don't know until we draw them. There are different possibilities. There are different possibilities. They might be parallel. Okay? They're not intersecting. If they are intersecting, 2 planes may be intersecting somewhere else, and the third plane is intersecting both of them from somewhere else. Okay? So you are right, in fact. But we don't know exactly what is the situation until we investigate about these equations further. Okay?
Okay, sir.
Any other question? Any other person who has some confusion? Or
सर इधर हम 0 से इक्वल टू 1 जब आ रहा है तो इधर हम फ्री वेरिएबल क्यों नहीं इंट्रोड्यूस करें?
बेटा 0 is equal to 1 equation बन रही है ना, which this equation is not a valid equation in mathematics. How can you say that 0 is equal to 1? How can you justify it?
But don't we introduce a free variable जब इस तरह की आती है situation?
No, we can't. If देखें यहाँ पे अगर ये दोनों 0 हो जाते हैं, for example, दोनों 0 हो गए, यहाँ पे भी 0 आ गया, यहाँ पे भी 0 आ गया. In that case, we are unable to find the value of Z because the third equation has been vanished. In that case, we say that we can introduce Z as a free variable. Okay?
Okay.
You got my point?
Okay. Yes.
अगर यहाँ पे भी 0 आ गया, अब in that case, we are unable to find the value of Z. In that case, we introduce free variables when we are not able to find values of the variables. Okay, then we introduce free variables. But in that case, when we have 1 here, okay, when we have 1 here and 0 here, that is not possible because you are saying that 0 is equal to 1, which is not possible in mathematics, which is a contradiction, which is not possible. So that's why your original linear system might have some problem, that there might be some modeling problem with that linear system. That linear system has not been constructed properly. You might have missed some physical property of something. You might have missed or miscalculated something in that thing. So it means the linear system which you have written is not properly modeled. So it has no solution, inconsistent solution. Sorry, inconsistent system. Yes, bole?
So inconsistent system में it could either be infinite solutions or no solution. लिया ये अभी तक हमने ये तो नहीं किया ना reduce के
No,
कौन
no,
सा
no, no,
है?
no. Consistent linear systems are those linear systems which have at least one solution. Either they have one solution or they have infinite range solution. Inconsistent systems, inconsistent linear systems are basically, they do not have any solution. They are not properly modeled, or that physical phenomena which you are basically trying to model is an ill-posed model. You can say that. Ill-posed model means there are some deficiencies in that model. You are missing something. You have not properly constructed that model. So that's why you do not have any solution. You have to change some physical conditions or some physical constraints in order to make that linear system consistent.
Okay.
Okay. मसलन मैंने आपको एक बनाना एप्पल की एग्जांपल दी थी, ठीक है? उसमें आप देख लें क्या सिचुएशन है. अगर पहले दिन जाते हैं आप बनाना और एप्पल के रेट डिफरेंट होते हैं, दूसरे दिन जाते हैं आप रेट डिफरेंट होते हैं, आप उसी से लीनियर सिस्टम बनाते हैं, वो तो लीनियर सिस्टम इनकंसिस्टेंट होगा क्योंकि आपका एक्स जो रेट है दोनों डेज में वो सेम होना चाहिए. देन यू कैन फाइंड द वैल्यू ऑफ एक्स. अब पहले दिन एक्स कुछ और था, दूसरे दिन एक्स का रेट मतलब बनाना का रेट कुछ और था, तो दैट इज नॉट अ consistent linear system. That is an ill-posed model. I hope you get it now.
जी sir.
Okay, Alizadi. It's time now to finish the lecture. If you have any further questions, you can ask me. Otherwise, I'm going to stop it here today.